So this is a video about Markownikoff's rule. So as an introduction, here we have a symmetrical alkene, and this is E-but-2-ene, reacting with a symmetrical reactant, in this case hydrogen. And because it doesn't matter which carbon one of the hydrogen atoms bond to, because the other carbon is identical to the original, we only get one possible product, and you can try this out yourself by drawing out the mechanism. Here's another example. We still have a symmetrical alkene, but this time we have an asymmetrical reactant, and we still only get one possible product because the bromine can bond to this carbon here. We get this possible product, and the hydrogen is on the other carbon. Or we can have the bromine on this carbon and the hydrogen on the other carbon, and we get the alternative product here. Okay, but these two are actually identical. These two are just well, that's just the same as this rotating in space. So with any symmetrical alkene, we only get one possible product in an addition reaction. Okay, however, if we look at an asymmetrical alkene with an asymmetrical reactant, we get two possible products. And you can try this out with different asymmetrical alkenes and different asymmetrical reactants. Here's another example. So this is hydration of propene. So we have again an asymmetrical alkene with an asymmetrical reactant, and you will get two different possible products. You can have the OH part of the water go on to this middle carbon, this carbon 2 here, to form this alcohol, or you can have the OH group here go on to the other carbon, and we get on the OH group on the first carbon here, and these are structural isomers of each other. So whenever we have an asymmetrical alkene with an asymmetrical reactant, we can get two different possible products, and we can show this in the mechanism. So here's our electrophilic addition mechanism with asymmetrical alkene and an asymmetrical reactant. So in this case, we should get two different products, or two different possible products. So we must have both the reactants being asymmetrical to have two different possible products. So the first thing that will happen is this pi bond will be attracted to the electrophilic partial positive hydrogen here, and the electrons will move from the middle of the pi bond to that partial positive hydrogen. As those electrons move towards hydrogen, the pair of electrons in the bond here will be repelled away from these electrons coming towards it, and the only place it can go will be towards the bromine. So we can have two different possible intermediates formed. So one of them could be where the hydrogen is bonded to this carbon, and the other one could be where the hydrogen is bonded to this other carbon. So remember, the pi electrons here, the pair of electrons forming the pi bond here, moves from this space to the space between one of the carbons and one of the hydrogens, or this carbon or this hydrogen. So there's a choice of two carbon atoms where the hydrogen can go. So we could have the hydrogen going on this carbon here. So there's the pair of electrons that came from the pi bond, and the other carbon that was forming the double bond would now be electron deficient, would have lost the electrons there, and it would have a positive charge. It's a carbocation. So the alternative is for the hydrogen to bond to the second carbon in the propene, and we have a different carbocation intermediate. So we have now the bromide ion, which is formed from the bromine in HBr gaining the pair of electrons to form a full charge, form a full ion. So this is not a partial negative. This is a full ion, and the pair of electrons we can show here. And those are going to attack the positive center on the carbocation. So now we have two possible products, which are structural isomers of each other, and we're going to use Markownikoff's rule to tell us which one of these will be in more abundance, because one of these will be produced with a higher yield than the other. So Markownikoff's rule says when an asymmetrical alkene reacts with an asymmetrical reactant, the major product is formed from the more stable carbocation intermediate. So we need to look at the relative stabilities of different carbocations in order to apply Markownikoff's rule. We can classify carbocations into either primary, secondary, or tertiary carbocations. Primary carbocations are those with the positively charged carbon attached to no other alkyl groups with no other carbons, or they could be attached to one alkyl group or one carbon. Secondary carbocations are carbocations with two alkyl groups bonded to the carbon with the positive charge. So here's some examples where the carbon with the positive charge is bonded to two alkyl groups or two other carbons. And here's one here. The positively charged carbon here is bonded to one and two alkyl groups or two other carbons. Tertiary carbocations are those where the positively charged carbon is bonded to three alkyl groups. And the relative stability of these three types of carbocations can be summarized as follows. Tertiary carbocations are the most stable. They are more stable than secondary carbocations. And secondary carbocations are more stable than primary carbocations, which are the least stable. So now that we know the relative stabilities of carbocations, we can use this in Markownikoff's rule and apply Markownikoff's rule to predict which is the major product and which is the minor product in the addition reaction between an asymmetrical alkene, like propene here, and an asymmetrical reactant, like steam. So in the hydration of propene, steam is the reactant. The steam doesn't look very asymmetrical here, but in fact in the addition reaction, the hydrogen is going to add to either this carbon here or this carbon here, and the other part of water, this OH here, is going to add up to the other carbon. So this is considered as an asymmetrical reactant. So let's practice again drawing our electrophilic addition mechanism. So the pi bond electrons here will be attracted to the partial positive electrophilic hydrogen here. So the electrons from that pi bond are going to move towards that partial positive hydrogen. As those electrons move towards hydrogen, the bonding pair of electrons here are going to be repelled away from there and move towards the oxygen. And the oxygen can accept those electrons, and we form a hydroxide ion. So as the bonding pair of electrons move away from the space between the two carbon atoms and towards the hydrogen, it will now exist between the space between the hydrogen and one of the carbons. Okay, so it could be this carbon or this carbon. So if the pi bond electrons move from the space between this carbon and this carbon here to a space between this carbon and this hydrogen, so here we're going to have this situation, and the carbon on this side here will have lost those bonding pair of electrons and will become positive. So we have this carbocation. So the alternative is for the electrons in the pi bond here to move from the space between these two carbons to a space between this carbon and this hydrogen, so it would be here, and we have this situation here, this alternative, and the other carbon would have lost the pair of electrons and become positively charged. So we have this carbocation. So this will be a primary carbocation intermediate because the positively charged carbon is only bonded to one other carbon. Whereas this one, this will be a secondary carbocation intermediate, as the positively charged carbon is bonded to two alkyl groups or two other carbons. So this one here will be more stable than this one. So this would exist for a longer period of time because it's more stable, whereas this is more likely to revert back to the original alkene. So there'll be less time for this to continue and react with the hydroxide or combine with the hydroxide that was left from the H hydrogen here breaking from this OH. So this part of the water gaining the pair electrons becomes hydroxide, which we got here. So this pair of electrons can attack that positive center, and we get propan 1O. And here we have the propan 1O. The secondary carbocation will be attacked by the hydroxide ion produced from the water undergoing hydrolytic fission. We have the hydroxide ion attacking that positive center on this secondary carbocation, and we should get propan 2O. So here's our propan 2O. We don't normally show the hydrogens on the skeletal, so I'll remove those hydrogens from there. As we said, this would be the major product, and this is formed from the more stable secondary carbocation intermediate, whereas the alternative product, which is the propan 1O, that is the minor product because it is formed from the less stable primary carbocation intermediate. So the wording would be as follows. So the major product, which was propan 2O, okay, so propan 2O is the major product as it is formed from the more stable, and this was a secondary carbocation intermediate. Whereas the alternative minor product, in this case, it will be the propan 1O. So, whereas the minor product, or alternative minor product, propan 1O, is formed from the less stable, and this was formed from the less stable, this bit, okay, that's the primary carbocation intermediate. So this is the wording you should use to explain which is the major product, which is the minor product. So the most common mistake people make is to say that the propan 2O is the more stable product, and that's not true. It is not the product that's more stable, it is the carbocation intermediate that forms the product more stable. So this is why we say the major product is formed from the more stable, in this case secondary carbocation intermediate, whereas the alternative or the minor product is formed from the less stable primary carbocation intermediate. So we don't say the product is less stable, it's the carbocation that made the product that is more stable. So we're comparing the stability of the carbocations in order to explain the abundance or relative abundance of the products.